Consider the following circuit consisting of an inductor, L, and a capacitor, C, with no resistance. This is logically called logically enough, an LC circuit. Assume the capacitor is charged to some amount Q0, but the switch is open so there's no current flowing. All the energy will be stored in the capacitor as 1/2 Q squared over C. But when the switch is thrown, current will flow. Will flow around like this, reducing the energy stored in the capacitor. But as the current starts to flow, there's a di dt, and so some magnetic field in the inductor will store energy as well. Let's look at the total energy. The total energy is going to be the energy in the capacitor, electric energy, plus the energy in the inductor, magnetic energy, and nothing else because there's no resistor, so there's no dissipative effects. There's nothing adding energy to the system, there's nothing taking out. So let's just figure out the derivative of this. The u dt would be the derivative of each of these with respect to t themselves, but of course c is constant and 1/2 is constant. So we get 1/2 times 1/c times the derivative of q squared, which is 2q dq dt. And likewise, I have 1/2 times L times derivative of I squared, which is 2I di dt. Yay for the chain rule. Of course, dq dt is just I. And so we have something like, we can, we have the 1/2 cancels the 2, I have q over c, and I have I. 1/2 cancels the 2, I have L times I, and then the second derivative of q with respect to t squared. Right? I can factor out these i's, and I get that du dt is q over c plus L squared d squared q dt squared, all of that times I. But u is conserved, so du dt is 0. So this whole thing is 0. The I we can divide out. It has to be true for all values of I. So we'll pick some non-zero value of I and then divide it out of the equation. And then we end up with L d squared q dt squared plus 1/cq equals 0. L times the second derivative of q with respect to t plus 1/cq equals 0. You should be able to convince yourself by now that this is solved by the solution that q is some number q0 times cosine of omega t plus some phase shift. In other words, exactly like the equation governing a spring and mass system. All right, it's exactly the same equation as we had, except that we had, of course, that it was m d squared x dt squared plus k times x equals 0. So we can see that it looks the same in form, so it has to have the same solution. And in fact, omega would have to be square root of 1/LC. Right? This is a spring mass system with no friction. In fact, we can set up the following analogies. In the block spring system, we have a spring that carries potential energy, 1/2 kx squared, and we have the block that carries kinetic energy, 1/2 mv squared, and of course, v is the time derivative of the position. The equivalent terms in the oscillator are there's a capacitor carrying electrical energy, 1/2 1/cq squared. Inductors carrying magnetic energy, 1/2 Li squared, and I is dq dt. The exact analogy between these two things. So we say q corresponds to x, and I corresponds to v, of course. And then, sadly, 1/c corresponds to k, and that comes down to way back in the dawn of time. Instead of saying q equals cv, we probably should have said v equals q times some capacitor. We should have just defined capacitance that way as like the thing that gives you voltage. Then we would have that the thing for capacitance-like thing would behave the same as the inductor and resistors do, because the other two are defined by the voltage is, R times I, or the voltage is L times di dt. And so we would have had that the voltage is some constant times the varying thing, but that's not what we did, and we're kind of stuck with it. So there we go. This suggests that our expression for the period, which for mechanical system was 2 pi root m/k, would be analogous to have an analogous partner in the electrical system, which is 2 pi root L over 1/c, that is 2 pi root LC. and it goes directly. It's an oscillator, just like a spring mass system is an oscillator, but it's an electrical oscillator. It's an analogy. This used to be the basis of the first generation of mechanical computers called analog computers, where you would literally take your physical system that you wanted to model, like a bridge system or a skyscraper, and wire an equivalent circuit by scaling and mapping the masses to the inductors and the resistances and so on over, and then running the circuit, which would run so much faster that you could see if there were instabilities or anything, and then say, oh, well, maybe I got to go back and fix my bridge or skyscraper or whatever. Here's just sort of an illustration of the life cycle. We start off with everything in the capacitor, and then some current flows around to discharge the capacitor. But as it flows through, as the current is flowing through the inductor and decreasing, because less and less positive is left on the plate, so there's less and less current, so it's decreasing, then we get inductance with some magnetic field and some electrical field and magnetic field. Eventually the capacitor is empty, and there's only magnetic field energy. But because the inductor is essentially like an inertia term, the current can't drop instantaneously to zero, so there's some there's some continuing EMF to counter that, which keeps it flowing. So there's actually too much charge. We pull extra positives off and deposit them down here, and some magnetic field. But of course that current does eventually die out, and then all the charge is stored on the plate, and it's the same energy as before, except the plate has switched polarity. And then we just go the other way around the circuit as the current flows the other way and grows, storing energy in this magnetic field until eventually all of it's in the magnetic field, and then it sloshes back and then goes forever around in that cycle. Things get interesting in a circuit that contains an inductor and a capacitor. All right, because some charge will leave the positive plate and flow to the inductor, but as the capacitor empties, the current will decrease, so inducing EMF in the inductor, and then some energy goes from the E to B field to the B. Eventually, the capacitor is empty and all the energy in the inductor, but Lenz's law prevents the current from dropping instantly to zero, so excess positive charge is pulled from the top plate, and the bottom plate becomes positive. The capacitor is swapped polarity, but then everything goes on, as I said, as before, and it sloshes back. And this oscillator, this circuit doesn't exponentially decay. It oscillates. All right? It goes back and forth in the same state. There's actually a connection here because what we'll end up doing here is that the mathematical form is really some sort of exponential, and when the argument is real, we get this oscillation. When the argument is imaginary, we get exponential decay. So there's sort of a mathematical reason for what's going on here. That's not terribly important or deep, but it's just interesting to know. The key thing here is that LC circuits are oscillators, so they can keep time. We can use them for timing elements in circuits to see that things happen at a certain rate.